to talk a little bit about like kind of what atoms do during chemical reactions. So we've talked about the fact that they rearrange themselves into entirely different chemical formulas. So you have something entirely different at the beginning than you do at the end. We talked about being able to count the number of atoms, but what are they actually doing? What in the world? So we're going to talk about how to classify chemical reactions by what the atoms are doing. The book does bring up redox reactions, acid-base reactions, gas evolution. We're not going to talk about those until later in the semester. It's good information to have. It's a good read. But I'm more worried that by the end of this chapter, right now specifically, that you're able to classify chemical reactions by what the atoms are doing, okay? So again, we're going to look at one kind of classification, but there are others, like what kind of chemistry is happening versus what the atoms do. Because we could have different kinds of chemistry happening in each of these categories, or we could have different kinds of reactions happening in each of those kinds of chemistry. So we're going to look at how the atoms have rearranged themselves from reactants to products to determine what category these things fit into. So you should be able to identify it using a chemical equation, a space-filling model, a ball and stick model, so on and so forth. You should be able to look at any of those different models of a chemical reaction and tell me what kind of chemical reaction it is. So the four kinds we're going to talk about are synthesis, decomposition, single displacement, and double displacement. So a synthesis reaction is basically exactly what it sounds like. It takes multiple different starting reactants and combines them to make one product. So in a synthesis reaction, we're taking multiple things, we're smashing them together, we end up with like one thing in the end. So we looked at this reaction going the other way earlier, where we created two water molecules from, broke two water molecules apart into hydrogen and oxygen. However, here we're looking at it in the other direction, we're considering it. So we're taking two hydrogen gas molecules, one oxygen gas molecule, and we're combining them together to make two water molecules. So two hydrogen molecules, one oxygen molecule combines together to make two water molecules. So I started with two different reactants and I got one product in the end. Same thing when I look at the second reaction on your screen. I have two carbon monoxide molecules reacting with an oxygen molecule so that it can make carbon dioxide. So and then down there, we're making potassium chloride. So we're taking solid potassium. We're going to run some chlorine gas over the top of it. And then by the end, we actually have potassium chloride as a solid rather than just strictly potassium. So again, a synthesis reaction takes multiple different starting reactants and combines them together to make one product. Decomposition reactions are kind of the opposite. So they take one starting reactant and they split it into multiple products. So the first one there is taking mercury oxide and splitting it down into, I guess it's mercury 2 oxide, I should be more specific. But that's mercury 2 oxide. So it's splitting that into mercury and oxygen molecules. We have potassium chlorate. So that's breaking into potassium chloride and oxygen. And then we have calcium chloride down there as calcium oxide and carbon dioxide. So again, you're just taking one starting product, you're breaking it apart into multiple parts. Okay, so next up we have single displacement reactions. So in single displacement reactions, one element moves from one compound to another. So the first one here, we have magnesium solid reacting with hydrochloric acid to make magnesium chloride and hydrogen gas. You actually did this reaction in the Evidence of Chemical Reactions Lab 2. We put that magnesium solid, we put it in hydrochloric acid, and we saw the bubbles being made. Again, down here, we have zinc and copper 2 chloride. So zinc and copper 2 chloride, if you react those together, you actually end up with zinc chloride and copper by itself. And we have the same kind of scenario down here at the bottom. We have two iron 3 oxides reacting with 3 carbons so that we can make some solid iron and some CO2 gas. So the idea there is we're just seeing that the one of the ions on the reactants is going to swap places when it goes to the products. In double displacement reactions, if you haven't already guessed, you're swapping both of the kind of anion-cation pairs. So before, in single displacement, we were kind of swapping it from reactant to the other reactant. Here, we're swapping the entire cation-anion pairs. So we're going to look at the compounds and switch both parts. So in this case, up here, we have silver nitrate reacting with sodium chloride to make solid silver chloride and sodium nitrate. So what we have here is we see that in the reactants, the nitrate is paired with the silver, but in the products, the nitrate is paired with the sodium. In the reactants, the sodium's paired with the chlorine, but in the products, it's actually silver that is therefore paired with chlorine. So we just swapped the nitrate from the silver to the sodium, and then when it took chlorine's place, chlorine went from the sodium to the silver. That's the idea here. So in this reaction, we're swapping the CO3 over to the hydrogen. We're taking the Cl, we're swapping it over to the sodium so that we have H2CO3 and 2 NaCl. And then lastly, down here at the bottom, we have barium chloride and sodium sulfate. So we have the barium with the chloride on the reactants, and we have the barium with the sulfate in the solids. In the reactants, we have the sodium with the sulfate, but in the products, we have the sodium with the chlorine. So in double displacement reactions, they just swap places. So here it is a little bit pictorially. We're using A and B and C and D to represent different parts of a chemical formula. So if we see two different chemical formulas coming together to make one new thing, that's synthesis. If we see two different kinds, or two different parts, two different kinds of elements in our chemical formula, and then those break apart from each other, we have a decomposition reaction. If we see that our one of our elements switches from one to the other, so how we have BC on the left-hand side and AC on the right-hand side, that C swapped from the B to the A. That's single displacement. However, if you swap both and you have two kinds of pairings, we have a double displacement reaction. So again, we see we have AB goes to AD and CD goes to CB. So that's a little bit how that works. So go ahead, go through, work through these as a practice, and see if you cannot determine if they're single displacement, double displacement, synthesis, or decomposition.